Hey everybody, I wanted to talk about juxtamedullary nephrons and different countercurrent mechanisms that are used to establish the concentration gradient in the renal medulla and what this means for ADH production, ADH secretion. So there are two main types of nephrons in the kidney. Most of them are these cortical nephrons, but I'm going to focus right now on juxtamedullary nephrons. The difference with these juxtamedullary nephrons is you have a very long nephron loop that extends deep into the medulla compared to this shorter one that you see with cortical nephrons. Also, the type of blood capillary that you see with juxtamedullary nephrons are these vasorecta right here. These are the types of capillaries you see associated with the nephron loop compared to peritubular capillaries, which are associated with more with the proximal and distal convoluted tubule of cortical nephrons. So we're going to focus on these guys, the juxtamedullary nephrons with the vasorecta and this very long nephron loop that extends very deeply into the medulla. One of the critical components of ADH functioning properly, and by ADH I mean antidiuretic hormone, also called vasopressin, you have to have a concentration gradient that is established in the medulla of the kidney. And this is established by the countercurrent multiplication system in the loop of Henle, or also called the nephron loop. The countercurrent exchange system is what will maintain this gradient, and this is due to the vasorecta, those blood capillaries. And then finally, urea recycling will help to maintain that concentration gradient. So first, the nephron loop, also called loop of Henle. Countercurrent multiplication occurs here, and it's because for the first time the reabsorption of water is not automatically coupled to solutes. With the proximal convoluted tubule, we saw a great deal of water reabsorption just by osmosis, and it follows salt. So we have obligatory water reabsorption just because it's following the salt that's being reabsorbed. However, this is not possible in the loop of Henle due to differences in permeability. The descending limb is permeable to water, but not salt, and the ascending limb is permeable to salt, but not water. So here is your renal corpuscle right here, and then you head into your renal tubule. Here's your proximal convoluted tubule, and then here is your nephron loop where we'll be focusing. Descending limb and ascending limb as you come back up. And then finally, here's your distal convoluted tubule here. These numbers that you see in here are the osmolarity that is present, and 300 milliosmoles is about what we see with blood plasma. So you can see before we head into the nephron loop, we're right about the same osmolarity as blood plasma. And as you head down, you see these numbers get bigger and bigger, and that is because the descending limb is permeable to water. So water continues to leave this descending limb because it's permeable to water, but notice no salt is leaving. So the salt stays within this descending limb, and you can see it gets saltier and saltier and saltier. Water keeps leaving, but the salt stays. So it becomes more and more concentrated the deeper you go down this renal tubule. You can see you're very concentrated down here, 1200 milliosmoles. As you round the bend and come back up, notice these numbers start going down. And that is because of a change in permeability. Here in the thick ascending limb is the location of these symporters. They're salt pumps. They're going to pump out sodium, potassium, and chloride. And they're actively pumping out these salts. And as salt leaves, then you notice these numbers going down. This is less salty as you go up the ascending limb. Notice no water is leaving. The water is not able to leave the ascending limb. Ascending limb is not permeable to water. So you're pumping out these salts, but the water stays. So you see it becoming more and more dilute. That's why the numbers are going down. And by the time you get all the way to the top and the beginning of this distal convoluted tubule, notice you have an even lower concentration of salt than you did initially. Osmolarity is lower than when you started. So this is what establishes your concentration gradient. You have a difference in permeability, and not only are you concentrating the interior of this nephron loop, notice this bar over here, the osmolarity of the interstitial fluid of the medulla is also increasing the deeper you go into the medulla. So not only are you increasing your osmolarity as you go down within the nephron loop, but also in the interstitial fluid. And this is why. So in the proximal convoluted tubule, you're constantly adding salt. Salt is constantly leaving the proximal convoluted tubule and headed to be reabsorbed in, but some of it will stay in the interstitial fluid. The higher the osmolarity of your extracellular fluid, ECF, due to this salt. So the more salt that's added, the higher the osmolarity. The higher the osmolarity, more salt, more water will leave. You have obligatory water reabsorption. You've got water leaving this renal tube, this nephron loop, and because it's attracted to the salt that's in the interstitial fluid. The more water that leaves, that departs this renal tubule, the saltier the interior of this nephron loop becomes. So more water leaves, now you're increasing the osmolarity of your nephron loop, it becomes saltier and saltier. The saltier the fluid in the ascending limb, the more this tubule is going to pump out these salts. So you see the sodium, potassium chloride, it's all being pumped out. So you pump out all the salt into this extracellular fluid in the renal medulla. And so that is going to contribute to the interstitial fluid concentration gradient. So in addition to increasing your concentration as you go deeper and deeper within your nephron loop, you're also increasing the concentration of the extracellular fluid in the medulla, in this fluid surrounding the nephron loop. And so this is countercurrent multiplication. And you can see this just goes right back around here. You have more salt that's pumped out, that's going to attract more water out of the descending limb. More water leaves, more concentration interior of your renal tubule, of your nephron loop. The more salty solute that you have in here, the more it gets pumped out and into the medulla. More salt equals more water pumped out from here. So you can see this multiplication, this positive feedback that's been established. So countercurrent multiplication is the first step. It's going to establish the concentration gradient in your renal medulla. Now, you need to maintain this gradient that's been established. You're constantly pumping water out the descending limb. In theory, that would dilute that concentration gradient you've just built, right? It's removed by the vasa recta. The vasa recta are going to be very important in maintaining this countercurrent exchange. Countercurrent exchange is going to involve the exchange of solute and water within the blood supply. So this is countercurrent exchange because you have fluid moving in opposite direction. So there's your countercurrent. One flow going down, one flow going up, and these tubules are very close to each other. And it's exchanged because you're exchanging salt from water. So here's blood from your efferent arteriole, right here, going down here. Remember, anything that is not filtered in the glomerulus, that blood will exit through the efferent arteriole. Next stop is vasa recta. So here's the blood from your efferent arteriole. You can see we start at 300. Salt comes in, water goes out. Salt comes in, water goes out. So you're exchanging water for salt. And so as you become saltier and saltier, you see these numbers go up. You're very concentrated by the time you get to the bottom of the vasa recta. As you come up the ascending limb, notice the exchange is going the other way. Salt is leaving this ascending limb of the vasa recta, and water enters. So you see these numbers go up, becomes more dilute as you send this blood toward the vein that's going to begin to exit your kidney. And this salt that you originally had brought in will just end up being deposited right back into that interstitial fluid of the medulla. So you end up reabsorbing that water that exits the descending limb of your nephron loop, ends up right in your vasa recta. So you end up bringing that water back into your blood, and you end up depositing all of that salt right back in the interstitial fluid. So that's why, in addition to the increasing osmolarity of your renal tubule and the vasa recta, you're also going to have increasing osmolarity as you go deeper into the medulla. So the vasa recta, these blood capillaries, will help to preserve, to maintain that concentration gradient. Finally, we have urea recycling. Urea is going to exit through the collecting duct and then diffuse into the thin segment of the ascending limb. Some of this will remain in the interstitial fluid, and that helps to contribute to the concentration gradient. So here is your collecting duct. You can see the urea leaving right here, and it will go up, 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 go along with that ascending limb of the renal medulla through the distal convoluted tubule and back down. And so you can see where the recycling part of urea recycling takes place. Exits here, enters into your ascending limb, and goes right back around. Some of it will exit. Obviously, some of it will exit into your urine, and you'll end up excreting that. And also, not all of it will end up into this ascending limb. Some of this urea will hang out way down deep in your medulla right here. So the urea recycling is going to help ensure that very deep in your medulla it stays the most concentrated. So the deeper you go, the more concentrated the interstitial fluid is, and that in part is because of this urea that's present very deep into the medulla. Otherwise, the salt that you end up depositing that we talked about with countercurrent multiplication, this salt would end up just kind of diffusing until it's equal. It's very important that the deeper you go in the medulla, these numbers go up. You become more concentrated, more salty, more solute. So urea helps to maintain that. So there's your three mechanisms that help to establish and maintain the concentration gradient of the interstitial fluid of your medulla. And you can see this lighter pink right here is your cortex. As you go into this deep pink right here, that is your medulla. So this concentration gradient is very important for the proper functioning of antidiuretic hormone. And this picture on the left is showing what happens if you are very hydrated. Very hydrated, you've been drinking lots of water, and so you're not producing ADH. Remember, the secretion of ADH is due to the osmolarity of your blood. Osmoreceptors are going to sense how concentrated your blood is, how hydrated are you, and then will secrete ADH appropriately. So if you're very hydrated, you're not going to have any ADH secretion. So countercurrent multiplication, exchange, this all stays the same. So water goes out the descending limb, salt goes out the ascending limb. Notice up here, by the time you get to your distal convoluted tubule, you are very dilute. And so all of this water that was stuck beginning down here at the bend of your renal tubule, all this water just stays in the distal convoluted tubule. It stays in the collecting duct. Notice we have very dilute numbers here, 100 milliosmoles compared to 1200 over here. So very dilute. And so you end up producing a large volume of dilute urine if you have zero or very low ADH, antidiuretic hormone secretion. So let's look over here at this picture on the right. So this is what occurs if you are very dehydrated, if you've not been very good about drinking your water, and you're very dehydrated. So countercurrent multiplication, exchange, that all is the same. So you see water leaves the descending limb, you have salt leaving the ascending limb. And right here at the beginning of the distal convoluted tubule, we're at the exact same place we were in the previous picture. If ADH is being secreted, its function is to add aquaporins, which are basically water channels, in this collecting duct. These aquaporins enable more water to exit your collecting duct so that you can reabsorb that water into your blood. So here's the location of aquaporin, here's a location. Wherever you see these arrows, that would be the location of an aquaporin that has been secreted due to ADH. So ADH binds to its receptors, you get aquaporins, more water is able to leave the tubule. Otherwise, water is not able to leave. It's not permeable. So water leaves the tubule thanks to ADH secretion. So water continues to leave, and you see the numbers in this collecting duct keep going up, 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 up. Imagine that there was no concentration gradient. Imagine that there was just 300 around here, just 300 all the way around. So here, when the interior of your collecting duct has reached 300, you would not have any additional water reabsorption at this point. You would not be able to get to 400, 600, 1200 within this collecting duct because you would have equal osmolarity. You would have no more net movement of water because even though you have these aquaporins, water is still just going to move by osmosis from an area of high concentration to low concentration. If the concentration is the same, if it's 300 on both sides, then that is as much water as you can reabsorb. No more water would exit. But because we do have this concentration gradient, the deeper you go, the more concentrated the interstitial fluid is. Then, as you have these aquaporins down deeper, down the collecting duct, more and more water is able to leave because you have a higher concentration. So, more water can leave by osmosis. It's attracted to all of this saltiness within the interstitial fluid. And as you go deeper, it becomes even saltier and saltier and saltier. And so you're continually able to reabsorb more and more and more water to the point where you're able to produce a very, very concentrated urine, 1200 milliosmoles, very concentrated and very small volume because all of the water has left the collecting duct. All water that you can possibly reabsorb has been reabsorbed into your blood. But again, the proper functioning of ADH is very, very dependent upon this concentration gradient. If you didn't have as strong a concentration gradient, you would not be able to absorb as much water.